So what we are looking at is the user interface of Turbo Design 1, which is the 3D inverse design code, and we will use it to design the impeller for the chiller compressor. So let me start by opening the input file that was exported from the mainline code Turbo Design Pre. As you can see, all these specifications here like the flow rate, RPM, etc. have already been filled in from the TD Pre file, and we can also see the meridional shape, which again comes from the mainline code along with this 2D grid which is automatically created. And the solver is actually a 3D code, and even though we don't have a numerical grid in the tangential or the pitch-wise direction, it solves the equations using discrete Fourier transforms, and that's why the code is very fast and is numerically quite efficient. Now we support different types of blade thicknesses such as normal and tangential, and in terms of type or the distribution, we have the simple constant thickness as well as more complex distributions like Naka profile and flexible control points. And actually this possibility to specify thickness as part of the inverse design is very useful because it guarantees structural integrity, and if you have some existing thickness profile, then you can import that as well using this option here. Now, blockage is something that we use for cases with significant boundary layer blockage such as transonic flows, and so we can skip that for now. And then we specify some fluid dynamic inputs, which is the blade loading, and this is the most important parameter for the inverse design method. Here we first specify the span-wise RVT star, which is the swirl distribution from the hub to tip. Here 0 span-wise location is the hub and 1 is the tip. And we are imposing the span-wise swirl distribution at the leading edge and the trailing edge of the blade row. So 0 swirl at the inlet means purely axial flow. And if you recall the Euler turbomachinery equation, the difference in RVT star between the inlet and the exit gives you the specific work of the blade row. And this is important because it means that every design coming out of TD1 respects your required duty point or the pressure rise. Now that the overall blade work is fixed, we need to specify how it varies from the leading edge to the trailing edge at the hub and the shroud sections. And for this we have the stream-wise blade loading, which directly controls the blade surface pressure distribution. So this is basically the derivative of RVT star, and it directly relates to the pressure jump across the blade. So here we have a parabolic section from the leading edge to a point here that you can vary, a linear section between these 2 points, and from this point to the trailing edge we have another parabolic section, and the loading at this point really defines the incidence at the leading edge. And at the trailing edge, the loading is always 0, which satisfies the kata condition. And so with these 4 settings, you can easily parameterize the 3D blade loading for manual adjustment or for automatic optimization. And then the last important parameter is stacking. And so on one quasi-orthogonal, you actually specify the variation of the wrap angle from and in that way you can lean the blade, and this will create a span-wise pressure force or gradient. And this is something that you can also use to additionally influence the 3D pressure field. But for now, we can continue with 0 stacking. And we can run the solver using this button here. Now, even though the program is fully 3D, it runs very quickly within half a minute or so, and it gives you the blade geometry and also quite an accurate inviscid flow information. And then this information is something we can use to iterate on the design. So once the solution is complete, we can first take a look at the converged impeller geometry using this 3D plot option here. And then we can also create 2D plots of, let's say, surface pressure at the hub and shroud. And as we will see later, when we compare surface pressure from TD1 versus that from CFD, we get a very good match, even though TD1 is inviscid. And that's because the viscous effects don't really impact the static pressure field. They do distort the velocity field, but we can relate the isentropic Mach numbers and isentropic velocities to some performance parameters, which we can use to explore the design space. And you can see these performance parameters here in the project manager window. Such as indicators of secondary flows, diffusion ratio or the profile loss, as well as some geometry parameters like throat and lean. And then under this UDP section here, you can also use Python scripts to develop your own specific parameters. And then finally, the selected design can be verified in CFD or FEA analysis. And for this, the geometry can be directly exported from TurboDesign 1 to different format files that are needed for mesh generation, such as curve files for TurboGrid or step files for ANSYS Mechanical.